Hello, welcome back. There's a handout today, which is another set of lecture notes, which is handout number 23. You should already have number 24, so I think we're up to date now in terms of sequence. A couple of notes from the TAs. One is that there is now an extra office hour, which is the hour before class on Thursdays, noon to 1 p.m., ERL 127. For those of you who found the existing office hours inconvenient. As usual, there will be a review session tomorrow, and that's televised on E1, I think, and it's in Skilling 193. And the topics tomorrow will be the third programming assignment, any clarifications for it, and going over the midterm. Everybody feeling comfortable with caches and cache strategies and cache algorithms and so forth? Now's the time to say so if you're not. The general picture that I like to keep in mind is this one, which is the kind of classic cache that's not fully associative and not direct map, but is a little bit of both. So if you keep that in mind and realize that direct map caches basically narrow it to a single width, and fully associative caches narrow it so that all comparisons are done in parallel. I got one email question yesterday which was interesting from an SITN student whose talkback circuit wasn't working, and that is, all of these things are powers of 2. Is there a reason why associativity is a power of 2? Is there some reason why there are 2 or 4 or 8-way associative caches and not other numbers? What do you think? Any opinions? Could I have a 3-way set associative cache with 3 sets of these boxes that I compare against? Kind of goes against the grain of computers that like to do everything in powers of 2, but would it work? No opinions. The answer is yes, it works just fine, and I'll show you a block diagram of a computer that does it. The number of sets has to be a power of 2 because you're doing this decoder based on some of the address bits. So the number of sets, the number of these horizontal rows, has to be a power of 2. But there's no reason why you couldn't have 3 or 5 or 7 or some other odd or prime number of blocks that and tags that you have to compare among to see if you've got a match. And an example of a machine just newly announced which does exactly that is the Alpha 21164. We can zoom in on this little picture part here. This, in fact, is from last month's issue of Computer Design. The 21164 has an 8K instruction cache down here and an 8K byte data cache down here. And one of the differences between the 164 and the 064 is that they have now added a second-level cache on the chip itself. And that second-level cache is 96K bytes. And the reason why it's a funny number like 96K bytes is because, in fact, it's 3-way set associative. That's how much area they could fit for bits and comparators and so forth. They really did not want to make these caches any bigger than 8K bytes, and we'll talk later today, I hope, about why it is that they've sort of run up against a fundamental limit. It has to do with the interaction between cache memories and virtual memory. They didn't want to make either of these things bigger than 8K bytes, but they wanted to reduce the miss penalty, because remember, this is a very deeply pipelined machine, and they don't want to suffer misses too often, so they put a level 2 cache on the chip itself of 96K bytes, and then there's a level 3 cache which the system designer adds in discrete SRAM chips on the board as external to the microprocessor. By the way, if you want to keep up with what people are really doing, then subscribing to something like Computer Design is not a bad thing to do, especially since it's free. Actually, if you fill out the subscription, I shouldn't say this, but if you fill out the subscription form and invent a company and make yourself vice president of engineering of that company, then you'll get a free subscription. Actually, I suspect that if you tell them you're a Stanford graduate student studying computer design, they'll probably send you a free subscription anyway, because they figure eventually you'll be important enough and they want you to know what's in the magazine. So that'll work. Of course, it's not very academic. It tends to talk mostly about what has recently been announced and what's really in the world, and lots of advertisements from people trying to sell you chips and so forth. But I think that's a good reality check to see whether some of the things that the academics talk about ever really get into the real world. What we're going to talk now about are some clever techniques for making these caches be even faster. And remember that there are three pieces that we could be making faster. The average memory access time, too many letters in there. Average memory access time for these things is the time to do a hit in the cache plus the miss rate times the miss penalty. And if you want to make the apparent speed of the memory go faster, then you decrease one or all of these three components. And we'll look sort of systematically at different techniques that make one or multiples of those components become smaller. What's fun about these techniques, like this one, the victim cache, is that they're really very simple ideas. And you'd think that caches, after all, have been around for 25 or 30 years, that all of the really simple, great ideas would have been invented already. But it's not true. And these are ideas that that were discovered, some of them at Stanford, just a few years ago, and they're now making their way into real microprocessors. And there's no reason they couldn't have been done 20 years ago, except that nobody thought of it. So I always find that encouraging, that you can enter a field relatively late, like you guys are entering the field, I suppose, and there are still lots of good, simple ideas that nobody's thought of that you might be the person to discover. So here's one of those. It's an idea to reduce misses, and it's called the victim cache. And you're going to become real familiar with this because it's part of the programming assignment. And the idea is that given a cache, in particular a direct map cache, add to it a small cache that might only have 4 elements. It's probably fully associative. It's basically there to catch things that fall out of the main cache. Anytime you have a recent discard for the main cache, you put it in the victim cache in a fully associative fashion in a kind of LRU scheme. So you throw things out, and it's easy to do perfect LRU in a 4-element cache. Basically what's happening there is that you're increasing the associativity of the particular set that you just discarded something from. So rather than increasing the associativity of everything in the main cache, which if you do it by a factor of 2 makes your cache twice as big, you're increasing the associativity, at least that's the way I like to think of it, as increasing the associativity of only the sets that you have recently referenced. So in particular with the direct map cache, where any time you have 2 addresses that map onto the same location, you're going to be losing because they will replace each other. With a victim cache of even only 1 block large, you wind up turning that into a win because alternate accesses to something that map in the same place in the main cache will hit in the victim cache instead, because the most recently discarded item will be saved. So basically, when you discard something from the main cache, you store it in the victim cache. If you look up something in the main cache and it isn't there, before going to main memory, or maybe even while going to main memory, you check the victim cache to see if it's there. And if it is, then you swap them. You put the thing that you found in the victim cache in the main cache, so you'll find it instantly the next time. And you are then discarding something from the main cache, and you instead put it in the victim cache. It's going to L2. So your model is this is L1 and L2 is main memory or something down there. Typically it is, especially if L1 is on the chip and the victim cache is on the chip. Then you've saved having to go off chip, which is a big expense in lots of ways. And if you don't have a level 2 cache and all you have is level 1 in main memory, then certainly a victim cache is a big win because it's in fast SRAM and the main memory is in slower dynamic RAM. Right. They tend to be. They tend to be even so slower, and they tend, yeah. So it's often a big win. In fact, I'm not sure whether the 21164 has a victim cache or not. I think it does actually. We'll look at the detailed block diagram of that a little later. At least the 064. Depending on the benchmarks you do, obviously your mileage may vary, but it can be that with a cache, especially when the main cache is relatively small, as level 1 caches on chips tend to be. If you have a 4 kilobyte direct map main cache and you have a victim cache with only 4 entries, some people have reported as much as 50% of the misses have disappeared because you've turned these misses that conflict in the main cache into things where you can recover and save the data in the victim cache. Yeah.
Cycle, so you don't, it's not like a cache miss.
Depends on your strategy. If you look them up in parallel, if you're looking it up in the main cache and in the victim cache at the same time, then in fact you might be able to get by without any penalty. Although you're going to have to cover for the cycle where you basically swap the element in the victim cache and the main cache. But sometimes, in fact, if you do it the naive way, check the main cache first, check the victim cache second, you'll wind up paying a bigger penalty if it's in the victim cache than it had been in the main cache. But still, it's better than going to the next level.
Question.
Yeah.
What does it mean by just 4 entries? 4 entries per mapping?
4 lines in the cache. There are 4 things in here, each one of which has a tag and a line, let's say 32 bytes of data. And there are just 4 of those things, and that's it. It's a cache that has 4 times 32 bytes in it, plus the overhead for the tag bytes. Might even be one line. Might be a victim cache that only saves the single most recently discarded line from the main cache. And you'll get a certain percentage of win just out of that. That answer the question? Okay. It's hard to see sometimes where these questions are coming from, whether they're here or gone. Okay, here's another great idea which you'll also be looking at for part of the programming assignment. And this is a way to get associativity when you're not willing to pay the price in the hardware to get associativity. So let's say that we have a direct map cache, and you do a lookup in 2 steps. The first step is you do, well, let me write it. If you start with an address, and you divide it into a tag part and an index part that you're going to use to look up in the cache, and here is your cache. You start using the normal function that you use to find an element in the cache, which usually is just taking the index bits and using it as the address into the cache. Right? But let's call that, to be consistent with PA3 terminology, let's call that B of the address. So B generates some place to look up in the cache to see whether that element is there. And in a direct map cache, if it's there, you win. If it's not, you lose. Well, the next step is let's try another location in the cache. If you fail to find it in the first location in the cache, let's, as a second step, do another function which winds us up somewhere else in the cache. Let's call that f of adder. Look it up in that location, and if it's there, you've won. Took you a little bit longer. You had to do 2 lookups in the cache instead of 1 lookup, but you found it in the cache and you didn't have to go to main memory. Now, probably what you want to do at this point, since this address is just recently executed, recently referenced, and our locality principle says that it might be referenced again in the near future, swap these 2 entries. So that the next time you look up that address, you'll find it on the first shot. You look at its first location. And the relationship between these 2 functions can be something which is really trivial. It can be, for example, flipping the high order bit of the address. So that basically you've divided the cache into 2 different halves, and you first check for the match in the first half of the cache, and if it's not there, you look at the corresponding location in the second half of the cache and check for it. And if it's there, then you do this swap. Now notice this has the nice property that B of 1 adder, well, I'll get into that in a second.
A question?
Yeah.
Those hashing functions have to be different enough so that you don't, by accident, hit the same location, same line for 2 different addresses? of one or the other functions?
You'll always be hitting the same line for two different addresses. That's a function of the way caches work, and those are conflict misses when you do that. These should be different enough so that B of an address and F of an address are guaranteed to be different. And in the simple case that you'll use, like flipping the higher order bit of the address, making it 0 if it's a 1 or 1 if it's a 0, you're guaranteed to pick a different location. So it's a very restricted subset of the kind of hashing algorithms that you may be familiar with in software techniques.
Can the B of one address be the F of another address?
You sure can, because that would be a conflict miss. If B of two different addresses may be the same, and those are two locations that are mapping onto the same place for the cache, and they're conflicting.
But
Yes, B of one will definitely be F of another address. In fact, we'll go over a case just like that in a second.
But it's not going to cause conflicts because you know that the first half is always straight and the other half is always translated.
No,
I mean,
some of the addresses may have their first hit in the second half of the cache. Is that what you're getting at?
What I mean is you wouldn't actually mistake an address by flipping the high order bit and therefore disguising it as another address that then you accept by accident.
Well, you'll never accept it by accident because you're always going to do a tag comparison to make sure that the word you're looking for is the word that's actually stored in the cache. So you can't make any mistakes. The idea of this is to get a hit speed which is almost the same as a direct map cache. Now, it's going to be a little slower in the case where you miss the first time and have to do another probe. In fact, it probably takes you an extra cycle. So it's almost the same as a direct map cache, depending on how often that happens. And a miss rate which is almost the same as a two-way set associative cache, because you're now, for every location in the cache, you've got two different places to check, which is exactly what a two-way set associative cache gives you. So it's a way to try to take a two-way set associative cache and sort of implement it in sequential operations rather than implementing it in hardware that does both of those operations at the same time. This shows that if you hit the first time, you pay a certain penalty. It takes you longer if you hit on the second time, and if you've missed on both of those times, then it's a long time to miss the cache. The idea here is that the direct map cache we know is easy and fast, but it has a hit rate which is some fraction of 100%. You know, in this picture it looks like maybe 60% of 100%. And that if we were to go to a real two-way associative cache with the extra hardware that requires, we would get some better hit rate. You know, it might be 75%, and the other 25% would be misses. And then this pseudo-associative cache sort of gives us a three-step process that we hit in the direct map cache the same rate that we would, well, we hit in the pseudo-associative cache at the same rate we would in the direct map cache on the first try. And the second try gives us all of the additional hits that the real two-way associative cache would give us, and then we miss the same amount of time. So one way to compute the average memory access time for this sort of three-step process is that it's one cycle, or whatever the time for a hit is, plus the rate at which the direct map cache would have missed times one cycle, say, if that's what it costs us. I'm sorry. Let me try this again. It's the time to do a hit if it would have hit in the direct map case, and you have to check that all the time anyway. And then the direct map case misses a certain fraction of the time, which is this. During that time, you're going to have to do the second check, and that's going to cost you maybe an extra one cycle. And a certain fraction of those cases, which is the cases that would have missed in the two-way set associative cache, you have to pay the full miss penalty. So it's a kind of three-component equation for how long it takes you to do this. Now, this is assuming that, in fact, this pseudo-associative cache gives you the same miss rate overall that the two-way set associative cache would.
A couple questions.
Yeah.
First of all, earlier you said that you don't need to, that you'll always know whether it was the right one by comparing the tag.
Right.
That doesn't seem to make sense because you can have two tags that match on these two lines, but because their indexes were wrong, they could have the, actually, it seems like you'd have to have a marker to say whether it's the primary or the secondary like they do in
Well, in fact, we are going to need a marker to say whether it's primary or secondary, but it's for a performance reason. It's not for a making it work right reason, right?
Okay, the second question is, yeah, aren't you assuming that you're not taking anything away from the two-way set associative by? I mean, it seems like there's more mappings than just a.
Right. What you're saying is that you think that, in fact, the hit rate won't be as good overall as the two-way set associative. In fact, you're right, absolutely. And in fact, this particular algorithm, as described, has a really fatal flaw in it that makes it terrible in some fairly simple cases. And the next slide tries to show that. That, as stated, that algorithm has a flaw with it in a very simple case where you try to reference alternate addresses, A1, A2, A1, A2, which is exactly the case where you want this pseudo-associative cache to work like a two-way set associative cache. It doesn't work. Let's say that the first hash address for the first hash location or lookup location for address A1 is the same as the second lookup location for address A2, and vice versa, which will of course be the case if we're doing this flip the most significant bit case. Let's take a look at a case where we're alternately referencing A1 and A2. Here, the first, this is one line in the cache, and this is another line in the cache. And this first line is the first place you check for A1 and the second place you check for A2. And the second line is the first place you check for A2 and the second place you check for A1. Right. So let's take a look at what happens if we're trying to add A1 and we've got X in the second line. We try to add A1 in the first line. Well, we look at its first location, which is the second line, and it's not there, so we missed on the first attempt. We look in the second location, and it's not there, let's say, and we add it. And then, what did I do wrong here? I'm sorry, we're adding A1. The first place to look for A1 is the first line, that's B of A1. So we look for A1, it's not there, we add it, and everything's fine. Now we want to add A2. The first place to look for A2, B of A2, is the second line. We look there, X is already there. Can't put it there. So we look at its alternate location, F of A2, which is the first line. It's not there, A1 is there, so we add it there. And then we're going to do this swap, because we want A2 to be referenced in a hurry the next time. So what do we do next time? We want to, let's say that it's not A2 to be referenced, it's A1. So we want to add A1. Well, we look for B of A1. Its first location is the first line. It's not there. X is there. We look for its alternate location, which is the second line. It's not there. A2 is there. So we put A1 there instead. And then we swap. And you can see what's happening. A1 and A2 are replacing each other, and X is not being referenced and is hanging around. So that algorithm doesn't work. It's amusing to think for yourself of the various ways you might patch up this algorithm. It's not a good idea to fix it by not swapping, because then if you have a sequence like A2, 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 you'll never get the fast cache access. You can't fix it by storing into the primary location if you miss in both the primary and the secondary location, because try it for yourself and you'll see that then a sequence like A2X, A2X, A2X will always miss, because they'll always be fighting for the same location. So there's really no trivial fix to this problem. The real fix is that, in fact, as you noted, you have to add an extra bit of state information to say whether or not a particular line represents the initial place it should have been or the second place you tried. And that's the so-called rehash bit that basically keeps track of whether or not this is in its secondary location and tries to guarantee that of the two cache lines that are related to each other, they are both not occupied by somebody in the secondary location. That's the fundamental problem.
What?
Yeah?
Why does A2 get stored into its secondary location when you miss on the second line? Add A2?
We tried storing it in its primary location, and that was occupied by X. So we looked in its secondary location, and that's occupied by A1.
Well, X is some other
X is something
existent
else.
element,
Right.
not don't care. Okay.
Right. And then, so it's not in its primary location. We look in its secondary location. It's not there, so we put it in its secondary location. If you think that putting it in its secondary location is not the right thing to do, and you should have put it in its primary location, that's this. And that doesn't work either. You really need another bit of state information to try to keep track of, to avoid the case where both of the lines are filled with things in their secondary locations. And the programming assignment has a flowchart that goes over it, and you need to study it and understand it. So it's something that you need to sit by yourself for 2 minutes in a quiet room to understand and make sure you believe that it works. In any case, I think next time in the review session, I presume the TAs will go over that and answer any questions. Okay? That's two little ideas for making caches go fast, both of which are relatively simple. The second one is not as simple as we had hoped, but it's still a good enough idea to make it worthwhile doing. Let's look now at another technique for reducing misses, which is prefetching. What we can do is that on a miss, we can fetch the requested block into the main memory, and then make an assumption that locality, spatial locality, means that the next blocks will likely be referenced as well. And have a special prefetch buffer, which may contain a cache line that represents the line physically after the one that you just put into main memory, or maybe a few of these lines. And basically what you're doing is trying to get the effect of a bigger block size. It has the same effect as doubling the block size of the main cache, but you're only doubling it temporarily for the one line that you just missed on, that you have to read into main memory, into the main cache. So just like the victim cache tries to increase the associativity for the most recent miss, prefetching tries to increase the block size for the most recent miss. Understand how that works? Basically, you miss in the main cache, you have to go to main memory. You bring that main memory line into main cache. The CPU is operating on it, and in the meantime, you take this path and prefetch the next line into the prefetch buffer. If you then miss in the main cache, you check the prefetch buffer. If it's there, then you win. You don't have to go to main memory. And if that's the case, you probably, again, want to do this kind of swap to make the thing that you prefetched go into the main cache and take the thing that was in the main cache and either put it in the prefetch buffer or discard it entirely. Another one of these simple ideas, takes very little hardware, can have dramatic effect, like removing 50% of the misses, even if you only have 4 prefetch blocks. Particularly works well when you're doing sequential accesses. So for instructions, it can clearly be a big win. For data accesses, it may or may not, depending on the sequentiality of data references. Okay. Well, the hardware designers shouldn't have all the fun. What is it that you could do in software to reduce misses as well? This is another one of these cases where you're willing to mix the architecture and the implementation of the computer design. And if the software knows enough about the hardware architecture of the machine, and particularly its cache structure, it can do certain things to make the programs run faster. One of them is that it can preload things that it expects to be missing in the cache. So it can do a load to register instruction before it needs to get it going. Or in fact, you might consider adding a special load to cache instruction. That's just an advisory message saying, I'm going to use this data eventually in the near future. If you've got nothing better to do, you might start making sure it's in the cache or loading it from main memory. In order for this to work well, it would be nice, and we'll talk a little bit about this later, that the cache be non-blocking in the sense that while main memory is fetching that data that you've asked to be preloaded into the cache, that you can continue on and make references to the cache for other things that are going to hit in the cache in the meantime. That's the non-blocking cache. lots of other ways you can change the basic memory reference pattern of the code. One is that you can make sure that the inline case of the code is the common case, and that if you're doing an if expression and then executing some block which is exception code that rarely gets executed, and then let's say the else clause that is something that's very commonly executed, you'd like to arrange the branches for the sequence so that this if part going to the rare code is off on the side somewhere, away from the area which is probably currently in the cache. And as long as you correctly predict the branch, and not taken is the right choice to make in that case, then you're not going to be making scattered references to instruction memory. You're trying to maximize the case where instructions are executed in sequence, and that maximizes the hit rate in the cache. There are lots of things you can do for data. For example, if you're referencing arrays in parallel, like you have an array of 100 elements and another array of 100 elements, and you're adding them together, or maybe these are 1,000,000 elements apiece and there are 6 of them and you're adding them together, you're bopping back and forth between an element in A and an element in B, which are separated by a long distance. One way to avoid that, and this is something which is hard for the compiler to do but easy for the programmer to do, is to combine those arrays, to merge them into an array, each of whose elements is a piece of the original array. So it's an array of 100 structures, and each element in that structure has one word of A and one word of B, so that when you reference them together, they're next to each other in memory and have a much higher chance of hitting in the cache. Another simple thing to do is to be careful of the order in which you access multidimensional arrays. If you have a floating point array, for example, which is A sub I j, and you do a for loop. This is no particular language, so I'm just inventing syntax here. If you say for I equals 1 to 100, and then another nested for loop that says for j equals 1 to 100, and then you make some reference to A sub ij, if you look at the sequence of references to the array I, there are 2 possibilities here. One is, if these are the different rows or columns of A, if you've made the wrong choice, then you're going to be referencing this element of A, the next reference will be this element of A, the next reference will be this element of A, and so on to the end of the array. And then the next time, when that inner loop finishes and you start the outer loop, you're going back to the beginning of the array, referencing this next location, then this next location, and this next location, and so forth. Basically means you're scattering your references all across the array. If you simply reverse the order and do the for j first and the for I second, then the references are to sequential locations in the array going from one end all the way down to the other end in one pass. It can make an enormous difference if the array doesn't fit in the cache in the number of, in the amount of penalty that you pay for referencing that entire array. Which one of them is right depends on the language definition, and which one of these subscripts varies most quickly as you step through the array. Different languages differ in that respect. Again, something which the programmer can do, I guess the compiler can do it too, but it's a little bit more difficult. And some languages mandate the order in which the array is physically to be laid out based on their subscript indexes. Other software techniques? Well, you may have 2 consecutive loops that operate on an array. You may have a loop that says do something to every element of the array, and another loop that says do something to every element of the array. And if you can arrange to have it happen that you combine that into one loop that does both of those things element at a time to the entire array, then you've made one pass through the array instead of 2 passes through the array. If the array doesn't fit in cache, it's a big win. The other thing you can sometimes do, depending on the numerical problem you're working on, is rather than operate on the entire array and go through it in sequence, perhaps multiple times, you may be able to break the array up into little subpieces and operate entirely for a while on one subpiece of the array, and then go on to the next subpiece of the array, operate entirely on that for a while, and thereby increase the amount of spatial locality in referencing the array. And if the subblock fits in the array but the entire array didn't, again, it's a big win. Those are some software techniques for making caches go faster. But we are not finished in what we can do with hardware. Let's look now at reducing the miss penalty. What happens if we go to the cache and we miss? We did the best we can in trying to reduce the miss rate, but there are still going to be some misses. How do we get the penalty we pay when the miss actually occurs to be as small as possible? Well, one, and we looked at this before, is to try to give priority to reads over writes. That don't make the whole machine stall when you're writing out to main memory, because you'd like to get other things like reads to occur in the meantime. And one simple way to do that is to have a write buffer. Rather than making everything wait while you do the write to main memory, stash it in a buffer, let it happen later. In the meantime, you can allow the system to continue to do reads. But as we mentioned before, you've got to watch out for read after write hazards to make sure you check the write buffer. Another thing we looked at, mentioned before, was this idea of subblock allocation. We talked about it in terms of miswrites and avoiding having to fetch from main memory when you do a miss by keeping individual tag words, valid bits for each of the subparts of the line. You can also do it to save on a read miss as well. If you choose this strategy, you could decide when a read misses only to read the part of the line, maybe the one word that the CPU wanted, set its valid bit, and leave all of the other bits set invalid. And thereby free up the path between cache and main memory to perhaps handle subsequent misses. Might be a win, might be a loss, depending on whether you've lost the opportunity to prefetch the next word, which is going to be the next thing you miss on. Another strategy is to, when you do a miss and are going to fill up the entire cache line, fetch the critical word first. Fetch the one that the CPU is actually asking for before you fetch the rest of the line. Remember that we've got a cache line here with multiple words in it. The CPU may have made a reference to the third word. If you follow the naive algorithm, you're going to say, well, this line, based on the address from the index part of the address, is not in the cache anywhere. I've got to fetch that line because the CPU wants it. You'll send a command to memory that says fetch this first, this second, this third, and this fourth. And the CPU can't get going until you fetch the third word. But you can decide instead to do a kind of wraparound fetch and fetch from memory first the one that the CPU wants, get it going, and in the meantime you can continue to fetch the rest of the words. That's this critical word first approach. The last kind of clever technique is to have a non-blocking cache. I mentioned that before, but basically it's a way to not to stall the CPU when you do a miss. And this especially works well when we're doing dynamic scheduling. When you've got multiple instructions that you're willing to execute anyway, if one of them stalls, you want to keep the other instructions that could be running executing, if at all possible. So you want to design the cache so that if it misses, it starts satisfying the miss by going to main memory and filling up the cache. But in the meantime, when it's waiting for main memory to provide the data, you should be able to accept subsequent requests from the processor on behalf of other instructions. And if you're lucky enough to have hits, you should be able to handle those hits while servicing the single miss. It's a big win, and especially in a machine that has dynamic scheduling. There are complications. One of them is whether you want to allow multiple pending misses. If you've got two misses, but there are instructions that could go ahead because their references will be hits, do you want to allow that? And if so, how many of these pending misses, you basically need a queue for all of the misses that are headed from the cache to the main memory. How many of those are you going to allow? So it can get complicated if you get carried away with this, but it can work well. Look at figure 6.21 in the book for some statistics showing in which cases non-blocking caches are a good thing to do. Okay, two more sets of ideas for reducing the miss penalty, and this is one that we've talked about on and off for a while now, and that's doing a two-level cache. If it's not in the first level cache, you look in the second level cache. And here again, the computation of the access time is that, well, you have to do a level 1 hit penalty, or a level 1 hit time first, which is also the time to see that it's not in level 1, so you suffer it in any case. And then some percentage of the time you go to level 2 and hit, and some percentage of the time you go to level 2 but miss, so you, at that rate, take a level 2 miss penalty. Now notice that this is based on the local miss rate. So this level 2 miss rate is the misses over the divided by the accesses to that cache itself, assuming that the level 1 cache is in front of it. Now remember, I made this mistake on the first set of slides that I produced. The solo miss rate, which is the miss rate that level 2 cache would have by itself, is a lot better. The local miss rate of that cache, of the second level cache, is typically very bad because the first level cache has already caught a lot of the things that the level 2 cache would have caught if it were by itself. So it's only getting sort of the dregs of what's left over from the level 1 cache. So the level 2 caches have, if you look at their miss rate, their local miss rate, it tends to be quite bad. Because that's true, you want to reduce the miss rate as much as possible. So the level 2 caches tend to be big. They tend to have big block sizes. They tend to have higher associativity. The hit time doesn't matter so much because most of the hits that the level 2 would have provided to you have already been filtered out by the level 1 cache. So what you want to do is to lower the miss penalty by keeping the miss rate down as much as possible. Well, there's another issue when you have two levels of cache, which is, does the second level cache, does the level 2 cache contain everything that's in the level 1 cache? Remember, our model is that we've got a level 1 cache, we've got a presumably bigger level 2 cache. Could it ever be the case that there are things in the level 1 cache that aren't in level 2 cache? Well, you could design a cache system to do that, but there are a couple of reasons why you might not want to. One is that it makes the analysis harder. If you've got this inclusion property, if everything in level 1 is also in level 2, then it's easy to compute the miss rates, because the miss rate of level 2 is the same as the overall miss rate. If you didn't have level 1 there, what leaks out of level 2 and you ultimately miss on is the same whether or not level 1 is there, because everything in level 1 is also in level 2. Right. That also means that the local miss rate of that this overall miss rate is the product of the local miss rate of level 1, those things that level 1 didn't have, and the local miss rate of level 2, those things that level 2 saw that it didn't have in it. So it makes analysis easier. But that's not a good enough reason. A perhaps better reason is that if this is a system with multiple processors, and let's say we have this is a processor making a level 1 cache request. If we have another processor making a level 1 cache request to its level 1, it has its own on-chip level 1 cache, and they're both making references to the same level 2 cache, you need this inclusion property to make sure that processor P1 is going to see in level 2 all of the things that processor P2 has in its level 1 cache. Remember, these caches level 1 caches don't necessarily have the same data, but by this principle of inclusion, we've guaranteed that everything in this level 1 cache and everything in this level 1 cache is in the level 2 cache. So they will see each other's data in the level 2 cache. And similarly, if you have I.O. making references to this level 2 cache, it will see the current data if this principle of inclusion is true. Now, what are the characteristics of a two-level cache that guarantee that this inclusion property is held? Well, this is one set of such characteristics. One is that the level 1 caches had better be write-through, because if they're write-back and the processor makes a change to something in the level 1 cache and it doesn't get into the level 2 cache until later, then obviously not everything in the level 1 cache is in the level 2 cache. So level 1 strategy has to be write-through. Another set of properties that guarantees that this inclusion is true is that the second level cache is larger than the first level cache, and that both levels have the same block size and the same associativity. If you think about it for a while, it's pretty obvious that if that's true, that the inclusion principle will be satisfied. These are more stringent requirements than necessary. Really, the issue is more complicated than that. There are other arrangements of level 1 and level 2 caches that still guarantee multi-level inclusion. You basically want the associativity of this to be higher than the associativity of this, and the number of sets in level 2 to be greater than the number of sets in level 1. But if you're really interested in thinking about those problems and convincing yourself what the general properties are that guarantee inclusion, then I suggest you take 382, where Mike Flynn talks about more of those issues. Questions about that? The 21164, whose block diagram I showed, does exactly this. It has a level 1 cache, which is a write-through cache, and in fact, I believe it has the same block size. It doesn't have the same associativity because the level 1 cache is direct mapped, but still, I believe, obeys this multi-level inclusion property, so that references from other processors or other I.O. devices only have to worry about what is or isn't in level 2. For the 164, that's still a problem, because notice for the 164, the level 2 cache is on the chip. So they do have an interesting problem of how to arrange multiprocessors that have this so-called cache coherence among level 2 caches, and they add extra hardware to make that work. A couple of other things for reducing hit time, more hardware tricks. One we talked about is to use a direct map cache instead of a associative cache, either fully or partly associative, because there's no multiplexer in the path, and because you can use the data speculatively while you're later on checking the tags. If it's a hit, you know exactly which data it is. That works well for reads. But as I pointed out earlier, for writes, that doesn't work as well, because you can't do the write, especially if it's a write copyback cache. You can't do the write until you've done the tag check to make awfully sure that the data you're about to destroy is the right data. There is a fix for that as well, and the fix for that is to pipeline the writes. You don't necessarily have to do the write immediately. Once you've done the tag check, you can delay the write into some time later. And one way to do that is to look at consecutive writes and say that, well, in the first cycle doing this write, I'm going to read the tag. But I'm going to delay doing the write to that cache until the next time I get a write. And during the next time I get a write, I'm going to read the tag for the second write, and then I'm going to take the opportunity to write the cache for the data on the original write. Basically, the tag memory and the data memory for the cache are split into separate parts, so you can be reading one and writing the other at the same time. So you basically don't spend an extra cycle waiting for the write to happen. Now, there's a minor gotcha here, and the gotcha is that this next write might take a while to occur. Right? So, in fact, there may be intervening reads in this sequence. Maybe I should draw it out to show how that works. Let's say I have a write here, and I'm doing a read of the tag. RT is read tag, to see if that write is in the cache. And in the meantime, I'm doing a write back for the I'm sorry, I'm not doing that. In the meantime, I have to save the data that I'm eventually going to be writing into the cache. So I do a cycle that saves it into a buffer. So I do a write into a buffer. Now let's say that the next operation on the cache is a read. Well, in a read, I'm going to use a read tag cycle, so I'm reading the tag. And at the same time, for reads, I can read the cache data. So I've got another operation here, RC, which is read cache. So for a read, I don't do any pipelining. I read the tag, I read the cache data for that tag at the same time, and if it's a hit, it's a hit. Everything has worked wonderfully. In the meantime, I've still got this data waiting to get into the cache that's sitting in the write buffer. Well, the next time I do a write, I can begin doing a read tag. I can do a write cache. I can take the data which is waiting in the buffer from this previous write and start writing it into the cache. So I've got another operation here, which is write cache. And at the same time, I write into the buffer. I buffer up the data which this write wants to put in the cache if it turns out the tag is a match for the next write cycle. So basically, you look at a subset of the accesses, those accesses which are only writes, and you invent this little pipeline, one-stage or two-stage pipeline that allows you to overlap the writing into the buffer with the reading of the tags, even for a write case where normally that wouldn't be allowed. But in the meantime, you've got to skip read cycles, which aren't pipelined. So it's a funny kind of pipeline where you've got a subset of the accesses fully pipelined in a two-stage pipeline, and another subset of the accesses not pipelined at all.
So it seems like it's more like a writing buffer. I mean, you're buffering the write.
Yes.
And I guess you're not going ahead and writing on the next cycle because you've only got one set of wires.
That's
and
right.
If you're reading, you need them to get stuff out.
Right. You've only got one read tag opportunity in each cycle. So if you wanted to elaborate your cache and allow you to do multiple read tags, or perhaps a write at the same time you're doing, or let's say you'd have to do a write of the data and a read of the data at the same time in order to be able to have the write pipelined on the next read cycle. So you could simplify this somewhat by adding more complexity in the number of ports to the cache. But this is a scheme that allows you to have the same effect only by adding a single write buffer and really not changing the fundamental cache itself. Now again, you've got to watch for read after write hazards because one of these reads might be reading the data that's sitting in the write buffer waiting to get to the cache. So you've got to check for that.
How does the last write get written?
There is no last write. Last write happens when you turn off the computer. Right? When is the last write that a computer will ever do? Now that's a kind of facetious answer. In fact, you may want to have stall cycles or no-op cycles that give you an opportunity to do that if you need to flush the cache, or there are some boundary marks that the software may have to impose to do task switches and things. So there may be a local last write. But generally speaking, the computer is never turned off, so there is no last anything. In fact, there are some operating systems who are designed to assume that the computer was never turned off or that you never have power failures, sort of like Unix. Right? You turn off the power switch on a Unix system, you're likely to have real trouble, at least on the older Unix systems, because disks aren't up to date, and so forth. Okay, new topic, which it turns out is not that different from caches, but it started out being different, and that is virtual memory. And we'll see, in fact, that virtual memory is just another cache, but its original motivation was quite different. Its original motivation was as a way to try to give the programmer more memory than really existed, to allow the programmer to write in virtual addresses and to map those to physical addresses, and so in a way that he has more virtual addresses than the memory has physical addresses. It's a great thing to do. It avoids overlays. It was invented back in oh God knows, 60s. I think Atlas was the first machine that had it, where real physical memory was very expensive compared even to CPU costs. And anything you can do to make it look like there's more memory than there is was a great win. If you don't do that, then programmers go through all sorts of contortions to try to overlay programs and data into a small address space. And this kind of thing, by the way, still exists. If you write in sort of real mode instruction environment for current PCs, you wind up limited to a 20-bit address space, and people are making a great fortune these days selling overlay software for PCs in 20-bit mode environment, the kind of thing that one would have hoped had disappeared 15 or 20 years ago, but didn't. It has a bunch of other advantages. It allows selective sharing of data between processes. We'll see that in a second. Because processes are talking to virtual addresses that get mapped into physical addresses. It allows you to protect data from the program and data differently from different programs. It allows you, without feeling guilty about it, to put big holes in your address space. Right? You can have an organization where you have a stack growing down from one side of the memory and a heap growing up from the other side of the memory. And most of the time, there's an enormous amount of big wasted space in the middle. And if that's virtual memory that doesn't really exist in physical memory, then you don't feel so bad. If you try to do that in a real mode machine that doesn't have that, then you've paid for and are wasting all of this memory in the middle that most of the time you're not going to use. Simplifies relocation. It's nice to be able to write all programs as if they began at location 0 in the machine and then fake it later by doing this memory mapping. And it allows you to start up programs in a hurry because you don't have to put into real memory everything that the program will ever need. All you have to do is put into real memory that part of the program that it needs to get going. And then it'll take page faults, as we'll see, to get the rest of that into real memory as it needs it. But really, all this is another stage in the memory hierarchy. Right? The real, maybe I should show the picture first to show how this goes. This is the sort of classical picture of virtual memory. Each process in the computer gets a virtual address space which goes to some high-order address, and this is typically big. This is 32 bits or 64 bits of memory, so it's 4 gigabytes, or God knows what 64 bits is, a lot of memory. And then there is some mapping mechanism, which we'll describe in great gory detail, for getting from an address in this virtual space to an address in this physical space. And the amount of physical memory is more limited. It might be limited to 32 bits worth architecturally, and it might be limited to less than that because of the size of the customer's wallet, how much physical memory he's really willing to pay. And these locations in physical memory can be allocated in any order. These are page frames. The memory in the virtual address space are broken up into big blocks, and we'll see why big in a second, called pages, and they can appear in any place in the physical memory in one of the page frames. And if they're not in physical memory, but they really do exist, they're not totally virtual, then they've got to be somewhere, and that somewhere is on the disk. And this is the sense in which virtual memory is simply another level of the cache. A subset of all of the memory in the system is in physical memory. That's a kind of level 3 cache, if you will. And the main memory, the place where everything exists, is actually out on disk. So this is now the main memory, and the physical memory is a level of cache holding the most recently used parts of main memory. Let me get a reality check here. How many people have seen virtual memory a zillion times before and know everything about it? Okay, it looks like we've got about half or so. I'll speed up moderately, but hopefully not enough to lose people who haven't seen this before. Okay, so this is one way of looking at this is just another kind of cache. Where the main memory, what used to be the main memory, the direct random access memory, is caching things for the disk. But it's got a bunch of quantitative differences that make significant changes in the strategies we choose for managing this cache. One is that the cache miss time is huge. The hit time might be, assuming that all of the other caches miss, the hit time might be something like 50 nanoseconds for a virtual memory considered as a cache. But the time for a miss is 10,000 times bigger than that. It might be 5 milliseconds because you're actually depending on access to a rotational device, to the disk, and you're waiting for this spinning piece of metal to get around to the right place. So because the miss time is so big, we want to do everything we possibly can to emphasize a high hit rate. So as a cache, we make virtual memory fully associative. Any block, and we're now calling blocks pages, can go anywhere in main memory. The other thing we want to do is to make the pages relatively large. One of the characteristics of the disk which is backing up this cache is that once you've paid this 5 millisecond overhead to get a byte out of the disk, it's almost for free or a tiny cost to get the next 1,000 or the next 4,000 bytes out of the disk. So as long as you're going to pay that penalty, you might as well get as much in at one time as you can. So that argues for making the pages large, or at least doing a lot of prefetching in the kind we talked before. But mostly it argues for making the pages very large. So what do we have? We have a fully associative cache with large pages. The total size of the memory is very large. We want, 16 megabytes and more to be accessible in physical memory. So if we were to implement a cache in the way we did fully associative caches before, which is to have a comparator for every line in the cache, you could never afford to buy that computer. There would just be too many comparators. So instead, we switched to a different technique for doing references to the fully associative cache, which is a table lookup. Rather than doing a comparator for every possible physical address in the cache, you have a table that represents every possible virtual address, and it tells you whether or not it's in physical memory. So there are essentially no comparators required at all. You turned it into a gigantic lookup table. But this is the kind of sequence of inferences here that lead you to the eventual design of the virtual memory system. That table is huge because the virtual address space is huge. Even if it were only as big as the physical address space, which is 32 bits, and the page size was still big, 4K or 8K, there are a huge number of possible entries that could get put in that cache. So you can't possibly spend the time or the space to store that entire table in main memory and look it up. So we have to use yet another cache to save the translations between virtual address and physical address. And that's the so-called translation look-aside buffer, or TLB. And we'll see in detail how that works. TLB is a terrible name, by the way. It's an IBM name. And other people call it a virtual memory address cache or an address translation cache, ATC, something like that, which makes a lot more sense. But IBM won out on this one. IBM likes to use their own terminology for lots of things, and most of the time, thankfully, they don't win, and the industry tends to pick other names. This is one case where they did win. They, for example, in years past, refused to have the word random associated with anything to do with their computers. Their marketing people decided that their computers were not random. They were deterministic machines, and they didn't want their customers thinking that they would do anything random. So where other people had random access memories, they had direct access memories. They had read-only storage instead of read-only memory. They used storage a lot instead of memory. And they had and have a lot of terminology that has tended not to make it into the mainstream. And eventually they're giving up on some of their proprietary terminology, but sometimes they win. One note on this memory mapping, page mapping diagram I showed before that I didn't mention, which is that it's easy to get a shared page. If you make the map so that two different pages in two different processes' virtual address space happen to map on to the same place in physical memory, then they're going to be accessing the same data, even though it appears at the same or at different places in the process's address space. So this might be memory location 1,000 for this process, and it might be 4,000 for this process, but in fact they're referencing exactly the same data. And that's usually an advantage, and it's sometimes a disadvantage, and we'll see later why it might sometimes be a disadvantage. Okay, what's the process for doing the address translation? Well, it's very much like doing cache lookup. You divide the address into two pieces. One is a piece which is the offset into the real page when you eventually find it. So this is a number of bits, which is the log base 2 of the size of the page. And then there's the other part, this virtual page number, which for caches we had further divided into a tag part and an index part. And in fact, we're now considering basically as one big index. We're going to take this entire virtual page number, use it as an index into this gigantic table that says for each possible virtual page, what is the status of that page? Number one, is it a valid page? Does this process get the right to use it? And is it in main memory so that it can access it at some location in real physical memory? So that's one of the sort of extra bits that has to get stored along with it. If it is valid, then the rest of the entry in this page table contains the real physical page number, the place where that page currently lives. You concatenate that with the leftover bits, which are the page offset, and you send that to physical memory. You might send that to a cache. We'll talk a bit about where the cache is in this process, but it might be, this might be a combination of cache and physical memory. So you do the address translation first, and then send it to memory. In addition to the bit that says that this is a valid page, you might want some protection bits that say whether or not I have a right to access this page, whether I have a right to read this page only, or to execute it, or to write it. If it's a page that I'm changing, and remember this is a write back cache, not a write through cache, then you have to keep track of whether or not that page is dirty, so that eventually when you throw it out of main memory and put it on the disk, you know whether it has to be written back to the disk or not. Virtual memory as a cache has to be write back or copy back, because if it were write through, then every time you made a reference to memory, you'd be doing a disk access, and your machine would be worthless. Another bit that turns out to be handy to have is a bit that just gets turned on when a process has referenced that page. And that's a way to get a sort of poor man's LRU. If you keep track of which pages have been recently referenced by turning on their reference bits, and then every once in a while the software comes through and sees which one of them which one of those bits are on, that set of pages represents the set that has been most recently referenced. And then it can turn off all the bits and wait another while and do it again. It's not perfect because of all of the pages whose reference bits have been turned on, you don't know in what order they've been referenced. You can only put them as a clump at the head of the least recently used queue, but it gives you a good hint. And since this page migration back to disk is hopefully happening at a fairly slow rate, it's a good enough approximation to LRU rather than having some very complicated hardware or software that keeps a perfect LRU match, perfect LRU list. Okay, one of the problems, one of the nasty realities of this virtual memory is that this page table, as I pointed out, could be huge. If you're using a 20-bit virtual address, because you've got a 32-bit address of which 12 bits are used for the offset into a 4K page, then you've still got 20 bits of address to use in an index into this table. And if each of those table entries is 8 bytes, then you've just burned up 8 megabytes worth of memory, presumably main memory, for this page table. And most of them are going to be unused, because this 8 megabytes of page table can represent 2 to the 32 bytes of virtual memory that your process, or most processes, won't be using. So how do you get around that? Well, one is that you could decide that on a sort of per process basis, you're going to limit the amount of page table it can have. So you're going to cut back on the amount of virtual address that a particular process can have. And there are systems that have done this kind of thing. it doesn't allow you to do this trick of having big holes in your memory space. So if you want to have a stack and a heap that's separated by a big space because you don't know how big each of those is going to be, yet you don't want to allocate that memory until it really gets used, you can't do it if you've set an absolute maximum on the virtual address space for a particular process. One way is that you could give up on this idea of indexing into the page table, and you could use more software kind of techniques and in fact use a hash table to do multiple probes into the page table to see. This is more like an associative cache in the old style that we talked about, where you do multiple comparisons to see whether or not the page table describes the entry that you want. In fact, it's more like the pseudo-associative cache, where you make a probe to see if it's there, and if it's not there, you look at another location. If it's not there, you look at another location. And in that case, the size of the table only has to be as big as physical memory eventually, or maybe twice that if you want to leave a bunch of holes. But still, it saves a lot of space, but it costs you enormously in time. Another technique, I mentioned up here that this 8 megabytes is probably in real memory. Well, in fact, it doesn't have to be. You can page the page table. You can put big pieces of the page table in places in virtual memory where in order to reference it, you have to use the page table. And if this sounds like it could be recursive, you're absolutely right. If you do this wrong, you could wind up in an infinite loop doing references to page tables and perhaps memory misses. If you're careful about it, it works well. And in fact, in that case, parts of the page table, especially the parts that are not filled up with anything valid that you're not going to reference, either don't exist or get written out to disk. So they don't have to take up precious real memory. You could try to combine the page table for multiple processes into one page table. That's not going to win you very much because you've still got the problem that an individual page table for a single process is enormous. The last scheme, which is one that, in fact, most of the architectures with very large virtual address spaces tend to do, is to use a multi-level page table. And the next slide shows how that works, and in fact shows how it's organized for the DEC Alpha. Basically, you still have this page offset. Down at the end are these, they have 8K pages, so their least significant 13 bits avoid the page table translation entirely and will be concatenated later onto the physical page number that this multi-level table will eventually produce. But instead of having 30 bits of address that you look up into one 2 to the 30th table, you divide this into multiple levels. Take the first 10 bits and use them to look up inside a page table that tells you where the next level page table is. And the big advantage of this is that you don't necessarily have to have next level page tables for every combination of 2 to the 10th bits, for every entry in this page table. And you might only have 1% of the possible page tables at level 2 actually allocated. And the ones that are not allocated are marked in the level 1 page table as not existing. No virtual memory in that particular place has ever been assigned to anyone. Question?
So that means the compiler is up front telling you what addresses or range of addresses you need so it knows what to allocate?
No, you don't have to do this in advance. You can start out with none of these page tables existing. And when you try to make a reference to some location, you'll get a miss.
So that's effectively paging the page table.
No, it's not paging the page table. I thought your question was, does the compiler have to tell you in advance which of these page tables? Right,
but if you're doing it real time, then you're sort of allocating the space when you need it.
That's right. You're allocating the space when you need it. You don't have to page the page table. You may want to wait to create the page table until you do a miss that says that you need that page table. And that's not as bad as paging the page table. It's deferring the allocation of the page table until you've demonstrated a need for it. You then may or may not want to decide to page those page tables. Typically for a scheme that has multi-level page tables, it's less necessary to do page table paging. So that wouldn't be done. We follow this on 3 levels. The first level tells you where the second level page table is. The second level page table can point to 1,000 different third level page tables. And finally, the third level page table can point to 1,000 different pages in main memory.
But as your memory usage increases, doesn't this degrade to sort of a straightforward page table where you just used up tons and tons of memory?
Absolutely. If you've in fact allocated all 2 to the 32 bytes in your virtual address space, and they all really exist somewhere, then you're going to need all of these page tables. There's no way around it. In fact, that rarely happens. It's unlikely that that would happen. And it's much more likely that this virtual address space has lots of holes in it for things that aren't used. And therefore you can get by with many fewer page tables than if it were all in one big table. But yes, in the worst case, it's in fact worse than having one page table, because not only do you have the sum of all of these level 3 page tables that have to describe all the physical memory, you've got to have these page tables, which at that point are pure overhead. The other problem with this, which we don't have time to discuss, but we'll in more detail later, is that look at what we've done. We've taken this highly optimized cache access to main memory, and in order to do a cache access, we now have to translate a virtual address into a physical address, and to do that represents looking up things in 3 different places in main memory. We could cache these things, but that's hardly a great win anyway. We've got to find a way to bypass this translation most of the time. And that way is the translation look-aside buffer that we talked about before. Before you leave, I want to point out that one of the homeworks, in fact, represents talking about, or involves understanding translation look-aside buffers and how they work. And although I've probably talked enough about them to let you solve that problem, I wasn't sure whether that was the case. So in fact, I'm going to delay the due date for the next homework from next Tuesday to next Thursday, March 9th. See you Tuesday.